Okay, questions. We'll start with questions and go from there. No questions? Then we will start with, let's start with that. So I will give you, this is from last time, I'll give you a few minutes. What would be, how would you fill in the boxes? Oh, yeah. You can discuss.
Well, you need a bit longer than It did be a backside in our supplement.
A strong nuclear file or a strong
So
base.
then,
And remember last time
I
we
would
talked
assume
about
it would
it
be
does one thing
CH2
with one
attached
that
to
does.
triple bond. Yeah, so just like,
Yes. Yeah, so the molecules that are, for the first one, the molecules that are on the arrows, those are the reactants. So you're reacting the alkynyl anion with each one of those. So you're reacting the alkynyl anion with each one of these halides.
I don't think it's I mean, you're just, I don't think it matters. And then with the fish, I remember, I think I can't remember reading in a book that if it's a tertiary, like it has E2 have an anti-tertiary or is that so there's the two makeup products.
No, but see, like, I have,
Right?
like this. So that would, do I not need to but I could just triple.
Or I guess there's only one because they're basically the same. I think we should have this
I'm gonna try that then. I think you're literally just adding, I mean, this is just like, like the essence. Yeah, I would just like top that off. And you would always, that's not
No, it is anti-periplanar, but it only have two like C groups attached to it. Whereas
that would be
there
C,
it had very small.
Can you reset to mine?
Because it doesn't like the H's can rotate, so it is.
So you can go like this.
So like if it's one of the branches,
Maybe draw it and
doesn't that the VR help to make it?
Is that what you want? So it wouldn't be here then?
This would go right here.
So you're adding this. Would it be a B
I just kind of maybe
would it be a PR version and then the page goes with yeah, but the line is
Okay, let's see how far we've gotten. All right, so on Piazza last night, somebody asked the question about how should, there are going to be problems, and there are going to be more of them, that as we go through the semester, it'll be like, okay, here's reactant going to product, going to the next product, with arrows, and you have to choose your reagents. So I did put on Piazza sort of an introductory, well, how do you approach that problem? So let's look at it for the first one, just in terms of the two things that you really have to think about in terms of approaching this problem. The first thing that I like to do is, what is in common with both the reactant and the product? So in other words, if I'm looking at this, I would say this part of the molecule is in the reactant and it's also in the product. So if you isolate that, even with a highlighter, you could say, okay, what's different about those two? Well, what's different is I lost the hydrogen. So once you identify what you're adding or what you're losing, the next thing I do is, what kind of reaction is that? So what kind of reaction is that first one? It's a deprotonation reaction. You could say it's an acid-base reaction. So it's a deprotonation reaction. So what needs to go in the box? A base. So last time we talked about the appropriate bases to deprotonate a terminal alkyne. And so what are my choices?
H2 minus or CH3 minus?
NH2 minus, or any carbon that's sp3 hybridized. So something like CH3 minus, and we'll get more into the CH3 minus molecules in the next chapter, because we're going to talk about Grignard reagents. Okay, but either one of those would work. They're going to come in, they're going to deprotonate. They're going to end up deprotonating the terminal hydrogen. So if you want to make sure your equations are balanced, and I don't care, then you would have something like NH3 on the other side. So first step is deprotonation. Now I made an alkynyl anion. The alkynyl anion now is our first molecule that is either a strong nucleophile, or it can also act as a strong base. The other molecules that will have those dual characteristics are going to be alkoxides. We specifically only dealt with sterically hindered alkoxides, although the book used something like ethoxide. We'll get more into that in the next chapter. So, strong nucleophile and a strong base. So let's take the left reaction first. What kind of reaction is this one? SN2? Do we agree that it's SN2? Okay, I've got a strong nucleophile. What kind of halide? Primary. So that would be an SN2 reaction. Primaries can only undergo SN2. So in this case, that's going to be an SN2 reaction. So what's going to happen? This C minus is going to come in, attack that carbon, kick the bromine off. And so what I have done is I've now added an ethyl group to the triple bond. And on Monday we said that reaction is also called starts with A. That's an alkylation reaction. Now, if that's where it would be, if I had just given you, let's say, the anion and this product and asked you to write the reagent, that's where you would take the same approach. Okay, what's common in both cases? I ended up adding an ethyl group, and you would say, well, I'm adding an alkyl group, so it's an alkylation reaction, alkylation SN2, and so it would help you with the reagents, help you narrow down the reagents that you would want to use. Now, the one on the right. As I was looking around, I don't know that I saw. Okay, so let's think it out. I've got a strong nucleophile, strong base with what kind of halide? Tertiary. So what does the nucleophile want to do? Act as a nucleophile. It wants to do an SN reaction. Can it do that with the tertiary? No. So what's it going to do? It's going to do E2. So that mechanism is going to be an E2 mechanism. Look, I've been doing this a long time. Every day seems longer and longer. But I expect the first time that you're going to try and do SN2 on it, which is what I saw. From here on out, let's try not to do SN2 on it. Although I will tell you, if I give you this on a quiz or I give you this on an exam, I'll still see some. So strong nucleophile, strong base plus E2 plus tertiary automatically goes E2, Sarah.
Why can't you do SN1?
I can't do, well, you can't do SN1 because this is not just a normal nucleophile, okay? This is a strong nucleophile that's also a strong base, so it'll do either one. But it's not going to wait around for the carbocation to form. So when things are strong bases like alkoxides and these alkynyl anions, they're going to act. So they're either going to do substitution or they're going to do elimination. And they're not going to wait around for a carbocation to be formed. So they really have no choice. And this is the first of these molecules that we've had. Right? This is the first of the strong nucleophile, strong bases that we've had. We'll have more. They have this dual characteristic. Their first instinct, though, is always, again, I'm giving them human characteristics, their first instinct is always to do substitution. But if they can't, they're going to immediately do E2. They're not going to wait. So they're immediately going to come in and deprotonate. So we're going to do E2. So now you have to remember from last semester, okay, what are the characteristics whenever we're going to do an E2 reaction? How are we going to start that? So if I'm going to do an E2, what functional group am I going to make? A carbon-carbon double bond. So where's the double bond going to go? Well, what do I need to identify first? The alpha and the beta carbons. The alpha carbon is attached to the leaving group. The beta carbons, in this case, are attached to the alpha carbon. That the beta carbons aren't the most important thing. What are the most important things? The beta hydrogens, and we have to make sure that each beta carbon has a beta hydrogen. I can make this a CH2 to make the beta hydrogen. So now I've got a beta hydrogen. So the space is going to come in, grab a beta hydrogen, pair of electrons moves, kicks the leaving group off, and I'm going to form a double bond. Our next step is, how many different products do I have? And can you draw them? Okay. So, take a minute, and then I'll ask you a number. How many different products you can form, how many unique products you can form, and then you can tell me which ones they are, and then we'll vote. We'll take it in that order. Number, identify them, then vote which one's going to be major. After we get the numbers, that's going to be the next question is, how do we want to look at it? Okay, so do we have numbers? How many different products are there? 2? I hear 2. Did I hear a 3?
Yes.
A 3, so I got 3, 2. Any other numbers? Okay, it's either 2 or 3. So let's vote. So if you have your little ABC cards, let's see if there's 2 products, we'll call that A. If there's 3, we'll call it B. So how many different products are there in this case? 2 or 3? You don't have one?
No, I left it on my desk.
Okay, what? I have one more, but it's my original, so I can't give you that one. So I guess you could go A or. How about this? A, B. All right, do I have answers, Tom? You don't have one either? All right, I'll bring more next time. I should have kept the one. Okay, so I see mostly A's, but I do see some B's. So let's write the different products that we can get, and the question is how many of them are unique. So let's call this A, let's call this B, and let's call this C. So it looks like that would be if I lost hydrogen A. That would be if I lost hydrogen B, which is down here. And then outside the ring if I lost hydrogen C. So again, we lose the H, we lose the Br, we form the double bond between the alpha and the beta carbon. So those are our 3 possible products. Are any of those the same? Which ones? A and B are the same. How do you know if they're the same? The easiest thing to do is name them. Or you can see if you can just rotate one into the other, which you could do by taking A and rotating it like this, and then it would become B if you rotated it. But they are both 1-methyl cyclohexene are their names. So A and C, or A and B here, are the same product. So they are the same. So there's only 2 unique products. Next question will be, what's the major product? A, I guess we're stuck with C. So your choices are which one is the major product, A or C, and I'll let you use D if you think they're both the major product. So which one's going to be the major product? A, C, or both would be D. What do we think? All right, I see A's and I see some C's and I see people not voting. It can't be B. Okay, so I see A's and C's. Why, if you chose A, why A? A is more substituted. And if you chose C, why C?
Because it's like, is it sterically hindered?
Okay, so hydrogen would be less sterically hindered to react with a more sterically hindered base, because it's acting as a base in E2. So whether you chose A or C is going to depend on how you view this alkynyl anion as a base. Is it small or is it sterically hindered? If it's small, it's going to give what product? A, because small bases always give the most substituted stable double bond. If it's sterically hindered, it's going to go after HC over here because that's the less sterically hindered hydrogen. So I asked that question. I asked the question not necessarily because I expected everybody to get the quote-unquote right answer, but to see what you think. Go ahead.
Do you have to take into account like the probability, since like you can get product A from 2 different hydrogens versus product C we can get from we can get from 3 hydrogens.
Okay.
Just keep that in mind.
No. So, but we might as well address that issue. Because in my class we did free radical halogenation at the end of the semester, we threw in statistics. But statistics only come into play in free radical reactions. They were never part of E2s. So statistics only come into play. So in this case, it's totally based on 2 factors. I'm going to form the double bond that's most stable, or I'm going to remove the hydrogen that's less sterically hindered. That's it. Statistics are not part of this particular reaction, but it's okay because we have to kind of redraw the lines and the rules for this. So the question is that a sterically hindered base or not? Well, the carbon-carbon triple bond is linear. Okay, so that means that if I did have any steric hindrance, it would have to be in this part of the molecule. It'd have to be way over here. And it's unlikely that if it was sterically hindered way over there, that it would make a big difference in terms of forcing the base. Now remember, when we talk about tertiary, the tertiary butoxide, we're basically putting a tertiary butyl group here. I can only put one group there, so if I put the tertiary butyl group way over here, it might be sterically hindered, but that's a methyl group. That's not sterically hindered. So in this case, we're going to treat the alkynes as if they're small bases like an H2 minus. That's how we're going to treat them. So that means the alkynyl anions with a tertiary halide, E2 is going to form the most substituted double bond. Did I say that in the video at all? I just did. So that's why I asked the question, was just to see where everybody was at in terms of their thinking. But that's the way we should think about this, is this is really not going to be sterically hindered at all. Okay, so we're going to get the most substitute double. But what you have to remember is alkynyl anions, tertiary halide are always going to be E2. So we have to go back to basics, identify the possible products, which one is most substituted. In order to identify the nature or the possible products, find the alpha carbons, find the beta carbons and hydrogens. Okay, so that's the reactions that we talked about on Monday. And there'll be more of those. The one thing we didn't talk about though is what happens if you react this with an alkynyl, the alkynyl anion with the carbonyl. And this is kind of foreshadowing what we'll see next week when we start reacting C minuses with carbonyls. So this is not SN1, it's not SN2, it's a new type of reaction. I already know that this C minus has to be a nucleophile. So what's it going to react with? It's going to react with an electrophile. So in this molecule, I need to find well, I already said it. carbon with the delta positive charge. I need to find the atom that has a delta positive charge that's going to act as an electrophile. That's the carbonyl carbon. This carbon is delta positive. The oxygen is delta negative. Why? Electronegativity difference in that polar covalent bond. Now what's going to happen? C minus is going to add to that carbon. But if we stop there, then that carbon's got 5 bonds. So something has to leave in order to form 4 bonds. Now, can these alkyl groups here leave as C minus? Oh no. Good time for review. What makes a good leaving group? In other words, what factors go into determining whether a leaving group is good or bad? One thing. Basicity. How? Inversely. So you want to know what a good leaving group is? Basicity. A poor base is a great leaving group. A strong base ain't leaving. So what did we say on Monday, or what did I say on Monday? No, we did it all together. What was the strongest base that we could have? A, C minus. So is this methyl group leaving as a C minus? No. Is this ethyl group leaving as a C minus? No. Are any hydrogens leaving as H minus? No, because H minus and C minus are comparable as bases. They're both really strong. Now, in the overall scheme of things, it's good that carbon and hydrogen are the strongest bases and never leave. Because all of organic chemistry is organized according to my carbon-hydrogen skeleton. I hang functional groups off of them and I change the functional groups. That's all we're doing, and that's all we will be doing this semester, is changing the functional groups off of the carbon-hydrogen skeleton. It would be really chaotic if your parts of your skeleton were just flying off left and right, including the hydrogens. So whoever came up with the basic rules of organic chemistry, either chaos or somebody smarter than me, pretty smart, it's organized that way. Those groups are not leaving. So that's the basics of, if space aliens come down and they say, organic chemistry, what's organic chemistry? Take carbons and hydrogens as a skeleton, hang functional groups off of them, change the functional groups. That's all we do. That's the basics of what we're learning how to do. So, they're not leaving. So what's left? How about I take this pair of electrons on the oxygen, on the CO double bond, and give it to oxygen? That's okay because oxygen is more electronegative than carbon, so it's more than willing to take the negative charge. So at the same time the carbon's attacking the carbonyl, the pair of electrons are going to the oxygen. Which means that what I'm going to end up making is I'm going to have my new carbon-carbon bond formed between the carbon and what was the carbonyl, carbon, and then I'm going to have an O minus. So this is a deprotonated alcohol, which is called an alkoxide. And we'll talk more about those. We already talked about tertiary butoxide, but this is what happens. So the alkyl group comes in, adds to the carbonyl. This is what we're going to call later on a carbonyl addition reaction. It's not SN1, it's not SN2. Kind of looks like a carbon-carbon addition, except I'm using a negative charge, not a positive charge. So, completely different. All right, so once I have this alkoxide over here, it just hangs out. Now you could say, well, why not? It needs a proton to go back to neutral. but I can't add the proton until the reaction's over with, because if I added this H plus, if I added that while I'm trying to react this, that proton's going to react with my alkynyl anion, and I don't have an alkynyl anion anymore, which means I don't have a nucleophile. So I do the reaction, then I throw in H plus. So the H plus then, and that's what the then H plus over the arrow means. It means this is a second step where now I'm going to add H plus, and what will happen is the O minus will react with the H plus, and I will ultimately form an OH. So I'll form an alcohol. And we're going to do this reaction over and over and over again when we talk about Grignards, which will be sometime either next week or early the next week after that. We're going to take C minuses and react them with all sorts of carbonyls. Okay? So that's the other reaction that you can do with an alkynyl anion. Okay? So that's, well, that was last time. So we did. That's what we talked about last time. Only this time we're doing problems in that. Okay. Does this make sense? Any questions? So there'll be more of these problems. If they're not in Top Hat, they will be coming for me. Okay. Now, the reactions for today, did anybody have any questions on the reactions? Topics from today? I'm going to review the new stuff if there are no questions, but I will answer whatever questions you have. So the difference in the reactions is this. All the reactions that we did with alkenes are, for the most part, applicable to alkynes, which is good if you remember them and not so good if you don't. Because if you don't, you're going to have to go back and review it. At the end of the little video I posted in Piazza, I talked about making a 3x5 card for reagents and two ways to structure it. One, the front of the 3x5 card saying reactant plus reagent and leaving the product blank so you can write down the product. And then the back, having the reagent and the product, but no, or reactant product and no reagent. Because unfortunately, you're going to have to kind of know both. You're going to have to be able to tell me what the reagent would be as well as write the product. And you'll see that in some of the problems that they have in Top Hat and that I will give you, where there'll just be arrows with no reagents. So you got to tell me what reagent would I use to make this product. And that's going to take some time to build up that skill. Maybe most of the semester. Maybe never, depends. But you have to kind of know forwards and backwards. My thing with the 3x5 card is, if I was smart, I'd just make them and sell them. But short of that, I suppose I could put them on a quiz book. But that's going to take time too. Don't expect that to happen. But the idea is that when you're going through your reactions, before class, after class, reviewing, constant review, if you really want to have them down. What you do is you can go through reagent plus reactant, and always write down your products on a whiteboard or a piece of paper. Never think, oh yeah, that's the right product, because you will tell yourself you get it right every time. And then you have to write it down and it's not right. So always write it down. But then after you go through your stack, you can flip them over and quiz yourself on the reagents. So that's my suggestion. If you have another system, again, I don't mess with student systems. If it's productive, you can use that. And I suppose you can make your own Quizlet if you wanted to. Or there's another one that starts with A that medical students swim. ANKI, I think. I think you have to pay for it if you have an iPad that's free on the computer. Anyway, when we're looking at these reactions, these are the same reagents that we use with the double bond. So you want to add two BRs to a triple bond, use BR2. Okay. So we're going to have to go back to our three questions. that we ask with every alkene reaction. What am I adding? What two groups am I adding? Am I adding the Markovnikov or anti-Markovnikov? Are they being added 100% cis, 100% trans, 50-50? So if you still have that up here from last semester, great, because you're going to use it with triple bonds. If you don't, you need to get it in there for both double and triple bonds. So we could add 2 BRs, or I could add 4 BRs. Because once I add 2 BRs, I'm going to end up with a double bond, and then I can add 2 more BRs to that. So with BR2, what am I adding 2 BRs? Markovnikov, anti-Markovnikov. Neither, because it's the same reagent. Cis, trans, 50-50. BR2 is trans. So you need to go back and remember that. When I started with the 3x5 cards, is because then somebody asked, well, should we go back and make 3x5 cards for last semester's reagents? Yes. I would start with new stuff and then it would work backwards. But, or whatever system you use. So we need that for triple bonds. HBr, I can add 1 or 2 equivalents. So the difference between a double bond and a triple bond is a triple bond has 2 pi bonds, I can add twice as much stuff. Same rules apply though. Markovnikov, 100% cis, 100% trans. If it goes through a carbocation, it's 50-50. So these are some reactions that we can do. These were new, well, 2 of the 3 of these are new for reductions. So this is a reduction reaction. These are actually 3 reduction reactions. Remember that a reduction reaction is when you add hydrogen. Okay, we talked about that both in lecture, and then when we did our yeast reaction last semester in lab, we added hydrogen, so we were doing a reduction there. So in this case, the triple bond has a slight twist to it, and that is that if you start with a triple bond, you can reduce it down to a double bond, and then you can further reduce the double bond to a single bond. So if you add 2 hydrogens, you can go to the double bond, and then 2 more hydrogens will take you down to the alkane, which I can just go ahead and add in the grand total of 4 hydrogens to get me to the alkane. The issue is that if you want to reduce an alkyne, a triple bond, to a double bond, first of all, you've got to stop at the double bond. So this reagent of the triple bond plus H2 and palladium, even if you decided I'm going to add exactly 1 mole equivalent of hydrogen gas, what would happen? The triple bond would be reduced to a double bond, and then that double bond would be reduced down to a single bond. So if you just added 1 mole of hydrogen gas, you would end up with some alkane, some alkene, and then there wasn't enough hydrogen to convert all the alkyne, because some of what was intended for the alkyne was used in the alkene. So what we do here is we just say, this palladium is a strong enough nucleus, or a strong enough catalyst, that it will reduce the double bond, which we saw last semester. So I'm just going to say, you know what, I'm going to use excess hydrogen gas, and I'm going to reduce that triple bond all the way down to a single bond. So if you use palladium and hydrogen gas, you will get the alkane, because we're going to assume that it's excess hydrogen gas. The critical part is, what happens if I want to stop at the double bond? Can I do that? And that would be desired to be able to do that. So the approach people use to stop at the double bond is, they said, Well, if the problem over here is that this palladium is just way too reactive a catalyst, let's kill it. Well, let's not kill it, let's poison it, is the approach that people thought of. And these kinds of catalysts are used in refineries. They're getting poisoned all the time, which leads to, they're very expensive metals, so you have to replace them every so often because they become poisoned. Let's use poison to our advantage. So Lindlar came up with the idea that if he took palladium metal and he mixed with that palladium metal a molecule called quinoline, which you can look up the structure of that in your book, along with some barium sulfate. If you put those with palladium, you poison it. And when you poison the catalyst, it can no longer reduce a double bond to a single bond. All it can do is reduce the triple bond. So Lindlar's catalyst, and there's probably other ones out there, basically will reduce the triple bond down to a double bond. Since the reaction is still occurring at the metal surface, the two hydrogens stick to the metal surface and then they add at the same time. So last semester we said, okay, H2, hydrogenation, what am I adding? Two H's. Markovnikov, anti-Markovnikov, neither because it's the same group. 100% cis because the hydrogen is sitting on the metal surface. So the alkene that you will make here is a cis alkene. So that was the approach that Lindlar used to figure out how to make a cis alkene. But then somebody said, because we need to have all the possibilities, right? I mean, if we're going to do synthesis, we want the yin and the yang, and we want, all the possibilities. So somebody said, well, can I make a trans alkene? Can you make the trans alkene? Yes, but you have to use a completely different mechanism. So these are all reduction reactions in general chemistry. Reduction means gaining an electron. The classical way to reduce something with a naked electron, adding that, you might say, well, why don't you just put an electrode in and put a battery in? Well, this predates batteries. And it certainly predates plug-in-the-wall electricity. So what happens is when you take sodium metal with its unpaired electron and you put it into liquefied ammonia, and liquefied ammonia exists at minus 35 degrees Celsius. If you liquefy the ammonia and you drop a piece of sodium metal into it, the sodium metal gives up its electron and the electron just runs around the solution. It's called a solvated electron. It has a very deep blue color. The solution is very deep blue. It's really spectacular, as long as you don't blow yourself up. Because liquefied ammonia, when it heats up, it becomes a gas. So there's actually a little condenser you use with dry ice. I've done this a couple times. Fearful for my life. You just have to put the gas in, it liquefies. You drop a piece of sodium in there. It's really cool. It's blue, and then you do whatever you need to do with it. This basically gives you an electron that will add to the triple bond. I think the mechanism was in the notes. I showed you the mechanism just simply because ultimately you end up with the carbons, one carbon having two unpaired electrons, so it's at the negative charge. The other carbon has one unpaired electron, so it's a radical anion. Those two lobes of density, each one is going to get a hydrogen. They have to be trans because you can't have two lobes of electron density next to each other, cis. So they have to be trans. So in this case, these are the conditions that you would use if you wanted to add two hydrogens and you want a trans double bond. I haven't looked this up, but I'm sure there's some YouTube video out there on adding sodium metal to liquid ammonia. But it's pretty, and the color is just, that's somehow how the solvate electron absorbs. It absorbs the right visible light to transmit the really dark blue color. Okay, so these are new reactions for reduction. Two of them are new. The thing you have to remember is if I want cis, kill the catalyst, poison it. If you want trans, you use sodium metal and liquid ammonia. That is different than NaNH2. NaNH2 is NH2 minus. So NaNH3 is a different reagent than NH2 minus. Okay. And then the only other reaction that is different is this reaction of adding H plus H2O to an alkyne. And this reaction is different simply because I look at this and I go, okay, I'm adding H plus H2O. What two groups am I adding? H, OH. How? Markovnikov. Okay, so that means the hydrogen's going to go on the carbon to the right, and the OH is going to end up on the middle, or on the carbon to the left. Okay, so there we go. I added an H and an OH. No different than I did last semester, except there's a problem. The problem is this molecule is half an alcohol, half an alkene. Therefore, it is called an enol. And for the most part, these run-of-the-mill enols are not stable. You go on and take PChem lab, you'll study enols that are stable. Okay? But these run-of-the-mill enols like this are not very stable. And so what they do is they undergo a rearrangement reaction to form a ketone. And the rearrangement reaction, the arrows look like this. We take this pair of electrons to form the carbon-oxygen double bond. We take this pair of electrons from the double bond to bond the hydrogen to the carbon, so that where we end up is we end up with a C double bond O. We end up with the hydrogen that was attached to the oxygen is now attached to the other carbon that was in the carbon-carbon double bond. And so that's a ketone. And so this is called a ketone-enol tautomerism. And we'll talk more about that. And we'll finish up this. The last part is just to set the stage for where we'll start. This is Markovnikov addition of H and OH. We'll have to remember how to do anti-Markovnikov addition of H and OH. Because if I do that, I'd be able to form an aldehyde instead of a ketone. But that's not BH3. So why do we use that? We'll talk about that on Friday. Okay? So on Friday, we'll finish this up. Go ahead and do the reading, watching video for the topics on Friday. We will start in-class quizzes over the previous material next week. So that first set of reactions that I gave you, that might be something I would give you as the beginning of class quiz next week. So you might want to get into the habit of reviewing your notes before you come to class.